rectifiers with filters. What is the necessity for these filters and what kind of filter it might be? For that, just let us go back to the basic block diagram of a linear power supply. See, what are the basic elements present inside a power supply, regulated power supply? If you look at so, first of all, we have the transformer, step down transformer, and whose output is Vm sin omega t, which we call it as a secondary voltage Vs of t. And after passing it through a rectifier, maybe half wave or full wave rectifier, okay, considering full wave rectifier, this is what we are getting. Let me call it as VO1, okay, which is a combination of AC and DC. And here the DC component is approximately equal to 2 Vm by pi. Of course, strictly speaking, slightly less than that. And AC component is more. And here we are passing this through a filter so that the output is known as a variable DC, which I have mentioned. How do you get this variable DC from this and what kind of filter it might be is my concern. Here, according to Fourier series, what we can do is this VO1 is a combination of DC component and infinite number of sine waves and cosine waves. And this part, infinite number of sine and cosine waves, this is called AC component. And it is anyway DC component. So our concern is to produce the best possible DC. Okay. And sorry friends, it is not regulated power supply, it is a DC power supply, linear power supply. Okay, it is converting AC to DC. Sorry, I mentioned regulated power supply. Okay. So, and coming to this, I need to remove the AC component or high frequency components have to be removed. Which filter performs this kind of operation? Definitely, it might be a low pass filter, which passes the DC signal and eliminates the maximum possible AC components. So that after the elimination of all high frequency components, the output is approximately like this. That's the idea. Here the filter we use is a low pass filter. Okay. And so far what we did, we connected the load resistor after the rectifier and we calculated some parameters like a ripple factor, peak inverse voltage, ripple frequency, efficiency, transformer utilization factor, etc., etc., percentage radiation and all. Now what I'm doing, the same rectifiers I'm analyzing in the presence of filter in between the rectifier and the load resistor. This is our case. And what might be this filter? It is a low pass filter because it eliminates all high frequency components and passes the DC signal. Okay, maximum DC we are expecting. It improves the DC level. Low pass filter will improve the DC level and reduce the AC level. Later we will see the regulator and all. Right? This is where we are at. So low pass filter means we know the basic low pass filter circuits. One is RC low pass filter and the second one is RL low pass filter. How does this RC low pass filter appear? Right, we are all well aware. We studied in networks and all. Right, I am not discussing too much detailed version. Just I am taking this low pass circuit. Input and output. What is happening? At low frequencies, the capacitor offers high impedance. So, if I take this loop equation, V in is equal to VR plus VC. Okay, so we know at low frequencies, impedance offered by the capacitance ZC is very large. impedance is large means even for a DC, the capacitor acts as open circuit so that entire input can be seen across the capacitor. Right? The current in the circuit will be zero. Once the capacitor is open, then the current will be zero and there is no voltage across the resistor. V output is equal to input, we can say. Okay, so at high frequencies, the impedance of the capacitor is very large and hence maximum signal can be seen across the input. Very large implies V output is approximately equal to input. As impedance is large, maximum voltage can be seen. So which means the entire input can be seen across the capacitor. And at high frequencies, ZC or the capacitor almost acts as short circuit, or ZC is very small and almost acts as short circuit and output is approximately equal to 0. So if the input signal frequency is low, that is appearing with less attenuation at the output. If the input frequency is high, that appears with more attenuation at the output. That's a simple principle, right? So now that's what we are doing here. If you right here, uh, any high frequency signal component is present at this point, that is not appearing after the filter, and any low frequency component comes, that is sent to the load resistor. That's the idea here. That's what is possible with this. And how does the circuit appear means, just we know this rectifier circuit, simple half wave rectifier. After that, how do we take this circuit? Low pass filter means we can use resistor and capacitor, but here not required. I'm directly taking the capacitor. So that what this capacitor does, after the diode, you can see the rectified half wave rectified waveform, and in that all high frequency components, for high frequencies the capacitor acts as short circuit, low frequencies it almost acts as open circuit. So only low frequency signals will appear, and hence the shape of the signal will change and it will be something like this. How it is coming and all we need to discuss. Of course, here at this stage it looks like a straight line almost. We'll see what is the analysis and all. So the capacitor is placed across the output terminals. Okay. And the second one is, we'll see, we have to discuss it. We are just at an introduction level only. Next one, RL, low pass filter, sorry. First one is RC, second one, it is RL. Sorry friends. It is RL, low pass filter. How does this circuit appear? Simply inductor and resistor. Input and output. So here, what is its working? Again, here I can take V input is equal to voltage across the inductor plus voltage across the resistor. So at low frequencies, what happens? Impedance offered by the inductor is very low, or almost it acts as a short circuit, so that output is approximately equal to input. And at high frequencies, the impedance of inductor is extremely high, so that almost all the input is seen across the inductor, and hence voltage across resistor will be very less. Okay, so almost open circuit. Okay, implies, so here what happens, VL is approximately equal to VI and VR or V output is approximately 0. And here very low means inductor acts as short circuit, almost short circuit. As it is acting as short circuit, V input is V output, or I can say VR, both are one and the same, is approximately equal to input. That's it. So any low frequency signal comes, the inductor pushes the signal to the output, load R, and if any high frequency signal comes, it holds it. So ultimately, you can see only low frequency signals across the output terminals. So that's a working of a RL low pass filter. Okay, so and how does the rectifier circuit with a filter appear? Means simply I'm just writing for half wave rectifier with a filter. So after the diode, we place the inductor next the load resistor. This is how the circuit appears. It is here a low pass filter. So rectifier with filter. Even the previous one, here I wrote it, but here practically there is a resistor. Even it is present as the resistor is in parallel with the capacitor, the overall behavior remains low pass only. Even overall behavior is like low pass filter. Okay, so let us discuss these filter circuits with the rectifiers. Okay, the first one, capacitor filter, which is very important compared to the inductive filter. Half wave rectifier with capacitor filter. This is how the circuit, as I mentioned. I'm not taking the load resistance for time being, just I'm placing here a capacitor so that what is it's working. You see, let me take this voltage as Vs and this as Vd, voltage across diode, voltage across the capacitor as my output. Okay, then if we take this circuit, I can write it like Vs is equal to Vd plus V capacitor or V output, nothing to worry about. And we have gone through this circuit actually. We studied it. Okay, where did we study? Right, because I explained the previous talk, right? Based on what we learned so far from the previous topics only, I'm trying to analyze this. You see, we studied the negative clamper. If you take the negative clamper, there what we did, we took a capacitor and a diode, remember? And here it is Vs, V capacitor and Vd. Here we wrote Vs is equal to V capacitor plus Vd. Look at this equation and this equation, similar. And one more thing, in this circuit, if the diode conducts, the current flows in clockwise direction. And here also, if the diode conducts, the current flows in clockwise only. Okay, so once you understand the operation of this circuit, the same thing. My concern here is, instead of taking the output across the diode, I am taking the capacitor voltage as my output, nothing else. This is my output. It all depends upon where you are taking the output. See, voltage doublers, voltage multipliers and all what we did. Every time we took the capacitor voltage as output. Because across the capacitor, you can see a constant voltage. The capacitor will charge up to the peak amplitude of the input. After the positive or negative peak amplitude of the input, later it acts as a diode becomes off and the capacitor acts as the DC source or battery. So we can see a constant voltage across the capacitor. Across the diode, what we can see a combination of DC and AC. So here my concern is to see the maximum possible DC which can be seen across the capacitor in a diode capacitor circuit. That's why what I did here is I have interchanged the positions of diode and capacitor. Very, very simple point. And working wise, same. I'm just repeating it for the sake of students. Okay, see that. I'm just taking the waveforms here. Just for our understanding purpose, I'm taking some 10 volts like that. 10 volts or 5 volts, doesn't matter. Vs is equal to Vd plus V capacitor. I have written 10 just for the better understanding sake. Okay, right. So here 0 to T by 4, what happens are before initially what I can take is 0 less than T less than T by 4, or before T is equal to 0. You can even write it. We have studied it at T is equal to 0 minus Vs is 0. Okay, Vs is 0 and diode is off, and assuming 0 initial conditions of capacitor. Okay, then voltage across the capacitor is 0, Vd is invalid, diode is open circuit. Vd is 0, Vs is 0, right? And for T greater than 0 or 0 less than 0 less than T less than T by 4. What happens once the input is a positive going signal, immediately the diode will be on. Once the diode is on, then ideally it acts as short circuit. Practically it offers a smaller resistance R, and the current will be flowing like this. So here what happens? The capacitor starts charging towards Vs with a time constant Rf into C rapidly. Okay, so the capacitor starts charging towards Vs rapidly with time constant tau C is equal to Rf into C. Okay, fine. And in this equation, I can write Vs is equal to Vd plus V capacitor. So Vd is almost negligible and V capacitor is approximately equal to Vs. We can take so. So that here, if you observe, Vd is almost 0 and the capacitor voltage is almost equal to our Vs. But always there is small delay. First the input rises, next the capacitor tries to capture the input. It follows the input. Then at T is equal to T by 4, minus Vs reaches its peak amplitude. In this example, some 10 volts. And due to small delay, V capacitor is not exactly equal to Vm. It may be some 9.9 volt like that, assuming ideal diode. Okay. Then for T greater than T by 4, or T is equal to T by 4 plus, right? I can write it. For T greater than T by 4, Vs is slightly less than Vm, and by that time the capacitor reaches the peak amplitude. Then what happens? Which implies Vd is equal to Vs minus V capacitor. It is 9.9 minus 10. It is minus 0.1 volt. It is negative. Whenever the diode experiences a negative voltage, immediately the diode becomes off. Once the diode is off, then what is our equivalent circuit? Like this. It is Vd, Vs, and the capacitor will charge with polarities like this. It is V capacitor. Right, which means here the anode voltage is like Vs is 9.9 volt, the voltage at the anode of the diode, and voltage at the cathode of the diode, it is 10 volts. That's the meaning of it. Anyway, the bottom line is voltage at the anode with respect to ground is 9.9, voltage at cathode with respect to ground is 10 volts. Okay. Then in that case, the capacitor can neither charge nor discharge. So once the diode is off, neither charge nor discharge, and simply acts as DC source or better. So how do we get the waveform? Already we studied this. The capacitor simply behaves like a DC source or better. Then what about VD? Whatever the variations you have in input, all those variations can be seen across the diode. Input falls by Vm and output also falls by Vm. And input further falls by another Vm, output also further falls by another Vm. Input rises by 10 volts, output will rise by 10. Like this. Input is peak, output is maximum at that time, and next input is minimum, that time output is also minimum. Like this we can see the things. Anyway, we are well aware the transient response, the transient state. This portion is transient. Removing the transient in steady state, here I am writing Vd is equal to Vm sin omega t minus Vm, and Vd, V capacitor or V output, what do you get? It is Vm approximately. Of course, if you take practical diode, Vm minus 0.7 volts. V capacitor is equal. Is it not a DC signal? The capacitor voltage is looking like a constant value of Vm. What else you want? Earlier, the waveform was like half sine waves, whose average value is 2 Vm by pi. In this example, what is the average value? Vm. Sorry, half wave rectifier. Average value was Vm by pi. Here it is simply Vm. So pi times the previous result. It's an excellent result. Okay. So this is how we can see the capacitor filters working. And here there is some issue, that is the peak inverse voltage. Okay. In this case, what is PIV? Important point to be noted. The peak inverse voltage PIV, it is equal to what is the peak value of the voltage across the diode under reverse bias condition? This much. This is the peak value. Here, during this portion, completely the diode is off. Once the diode is off, what is the peak voltage the diode is experiencing under reverse biased condition. That is PIV, it is equal to, what is this value? It is minus 2 Vm, or it is 2. This is the drawback. Okay, the drawback of this circuit is this. Other than that, you can see the best possible result. Okay, that's it. This is how we can see. But the thing is, practically speaking, always RL is a must. Once we are designing a system, means always its output is meant for driving some other system. That some other system is in general denoted by a load resistor RL. So that this is the practical half-wave rectifier circuit with capacitor. Practically RL is present. Of course, we can write RL and capacitor, we can even interchange the positions, doesn't matter. Okay. So what is its working? Let us see. It is Vs, capacitor and resistor. Okay, as usual, when Vs is 0, that time diode is off. Assuming 0 initial conditions, capacitor voltage is 0. Everything is fine. At t is equal to 0, Vs is 0, diode is off. Assume 0 initial conditions for capacitor. Okay, next, as usual, from, right, let me write the same waveforms here also. Vs, just I'm taking the peak amplitude as 10 volts. Actually, only with RL, what do you expect? Okay, full wave rectifier. I'm writing just half wave rectifier. Only if RL is present, then this is how we expect the waveforms. Okay, let me take this interval, this instant, as t by 4. I need not worry about VD, right? I'm just looking at what's my output. Okay, so 0 to t by 4, as usual, 0 less than t by 4. As usual, diode is on. Once the diode is on, what is the equivalent circuit? Almost the diode acts as short circuit. Practically, it offers a very small resistance. Okay, however we read, it doesn't matter. The diode forward resistance. Yes. So this is then further written like, what is it? So Thevenin's equivalent resistance. It is just nothing but RF parallel with RL, or approximately equal to RF. Which means the same circuit can be even redrawn this way. So then it is similar to the previous circuit, which means the capacitor will rapidly charge towards Vs with time constant Rf into C. The time constant of this circuit, we are well aware how to find its equivalent time constant. Okay, implies the capacitor rapidly charges towards Vs with time constant tau c is equal to Rf into C. Okay, it is charging. Like this. Okay, and at the same time, here at t by 4, I am taking the same story I am repeating here also. At t is equal to t by 4 minus Vs is equal to 10 volts, it is at its peak amplitude, and V capacitor is equal to 9.9 due to small delay. Here also what we can write in this circuit, anyway, Vs is equal to Vd plus V capacitor. The equation doesn't change. Here also Vs is equal to Vd plus V capacitor. Vd is neglected, so V capacitor is approximately equal to Vs. The same story only. Okay, and due to small delay, okay, at t is equal to t by 4 minus Vs is equal to 10 volts, and due to small delay, V capacitor is equal to some 9.9 volt. And for t greater than, at t is equal to t by 4 plus Vs is just falling below its peak amplitude, and by that time the capacitor reaches 10 volts. Everything implies, what about, or implies Vd is equal to Vs minus V capacitor, 9.9 minus 10, it is equal to minus 0.1 volt. Implies diode is immediately off. Once the diode is off, what is the equivalent circuit? Is it possible to write so? No, the things will change. If the diode is on, then you can write the equivalent circuit as Vs and Rf capacitor. Now, once the diode is Rf, the diode reverse resistance is infinite, and this RL comes into picture. This is how we can take it. Now, what happens to the capacitor? Okay, earlier there was no path for the capacitor neither to charge nor to discharge. Now we can see a path for the capacitor to discharge. I can say like this. So what we can write from this circuit means, now the capacitor starts discharging through RL with the time constant tau d is equal to RL into C. That's it. Means here, if you observe this waveform, the capacitor starts discharging like this. See, charging is rapid because charging time constant is Rf into C, whereas discharging is slow. Okay. And just as an example, I'm taking the capacitor is anyway slowly discharging like this. And after some time, meanwhile, what the input is doing, it's not keeping quiet, it's doing its duty. It is coming down to negative peak. Again, it is rising, reaching 0. Again, it is good. Just for our better understanding sake, I'm taking, for example, the capacitor has, right, capacitor voltage has come down up to 8 volts. But whereas the input is rising, see, the output is decreasing and input is rising. Output is decreasing almost linearly, exponentially, strictly speaking. Exponentially, it is decaying. Input is sinusoidally rising. Input has come down to negative peak, later it is rising. So, at this particular instant, what happens is input is going above 8 volts and V capacitor is falling below 8 volts, which makes the diode to conduct. Input means the anode voltage, capacitor voltage means the cathode voltage. So, anode voltage of the diode is going above the cathode voltage, and hence the diode again starts conducting. So, let me take this time as T2. Just I am writing it. At T is equal to T2, Vs increases above 8 volts and V capacitor falls below 8 volts. Implies immediately the diode starts conducting. Again, the diode starts conducting means what is the equivalent circuit? The equivalent circuit is that's it. Which means we are well aware this is of course equivalent to this one. Okay. So what we can expect here? The output waveform. Again, the capacitor starts charging towards Vs. Almost Vs, capacitor voltage follows Vs. And this will continue up to the input reaches its peak amplitude. Whenever input falls below its peak amplitude, by the time the capacitor voltage reaches 10 volts. Okay, let me take this instant as delta t. Means it is a T2 plus delta t, I can say. Okay, at a T2 plus delta t, at t is equal to T2 plus delta t, Vs falls below 10 volts and V capacitor reaches 10 volts. Implies the diode becomes off. Means the anode voltage below 10 volts means Vs means it is just nothing but anode voltage, and V capacitor it is just nothing but cathode voltage of diode. So diode becomes off. We know once the diode is off, what is the equivalent circuit? So again the capacitor starts discharging. That's it. The same story repeats. So whatever has been taken place, right? Whatever has taken place from here to here, the same story repeats from here to here. And here the output is decreasing exponentially and the input is falling down to uh, its minimum value, and sinusoidally further it is rising. So at 8 volts, when V capacitor falls below 8 volts, by the time input rises above 8 volts, and again the diode starts conducting. Once the diode starts conducting, means again the capacitor will rapidly charge towards Vs with time constant R. Okay. And when V input reaches its falls below its peak amplitude, by the time the capacitor voltage reaches 10, then again diode becomes off and the capacitor starts discharge. This repeats. Initially it starts with 0 only, but after one cycle what happens, the capacitor voltage is switching between, right, once the diode is on, then the capacitor will rapidly charge from 8 to 10 volts. And when V input falls below its peak amplitude, that time diode is off and the capacitor will slowly discharge from 8 to 10. When V capacitor falls below 10 and input rises falls below 8 and input rises above 8, again diode starts conducting and rapidly it charges. That's it. So this part repeats 8 to 10 and 10 to 8. That's it. So if you observe in steady state, right, this is what I can take it as transient. It may be some 8 volts like this. So initially the capacitor will no doubt starts charging from 0 volts only. After that it charges only from 8 to 10 in steady state, I can say, and it discharges from 10 to 8. So we can see the steady state response this way. Okay, the capacitor voltage is something like this. Output voltage. Okay, this is the idea, and how it is improving the DC level is my concern. Okay, you just take the dotted line. What is the average value of this dotted line? We studied its average value is if its peak amplitude is Vm, then its average value is Vm by pi. We are well aware. In a class, if the marks are varying like this, right, like half wave rectified waveform, we studied the average marks of the class will be Vm by pi. Now you see the second case. What about the average value of this? In a class, if the marks of the students are varying like this, the average percentage will be in between maximum and minimum. Here, some students are getting 0 marks, but here the minimum mark itself is this much. So what about its average value? If you take it so, the average value lies in between maximum and minimum. This is VDC, which is much better compared to VM. Is it not so? Okay, this is the idea. We are improving the DC level. Okay, right. And one more point here, the value of RL, right? It may be small or large, we do not know. One thing we can say is compare it to a simple basic half wave rectifier whose average value is Vm by pi. This half wave rectifier with capacitor filters, output is changing, accordingly its DC value is also changing. It's good, no doubt about it. Okay, and here what is the role of this load resistor RL? All right, why did I keep it? If RL is not present, directly you will get VDC is equal to Vm. That's what that's where I started actually. Okay, then what is the role of this RL? What it is? It's a must. We can't do anything. Now just for understanding of the understanding the role of RL, let me take the case like this. Just for understanding sake, I'm writing. Here, RL1 is less than RL2 is less than RL3. I'm taking three cases here. See, if the time constant is small, if a load resistor is small, then what happens? Definitely, the discharging time is also will be less, no doubt about it. This is what you can see for the first case. Okay, so here RL is small, then capacitor will rapidly discharge. It not only rapidly charges, but it will discharge rapidly. Here, tau d discharging time constant is RL1 multiplied with C. Second case, right? Compare it to RL1, RL2 is larger, so definitely discharging. It will slowly discharge compared to the previous case. So if I take the second case, this one, okay, so definitely the capacitor will discharge bit slow compared to the previous case. That's why the discharging time is something like this. This is tau d2 is equal to RL2 into C. Compared to this, the third one, we are choosing much larger value of R. So definitely the capacitor takes more and more time. So here it is a tau d3, it is equal to RL3 into C. And further last case is also if RL approaches infinite, then what happens? It is a tau d4, it is equal to RL4 into C. RL4 is very large, almost like infinite, means open circuit. Then in that context, it looks like output looks like a straight line output voltage. So DC level will be extremely high. We can see. Okay. So and anyway, in all these cases, the charging time does not change. If you observe, so this charging time is from here to here. The same time you can see here also. The charging time does not change, but the discharging interval keeps on changing depending upon the value of R. Okay. So here it may be some, just as an example I am writing here, it is okay. Starting with 0, it's a transient response, it is shown. Or here it may be due to smaller value of time constant, it may come down up to 6 volts, or here it may be coming down up to 8 volts, 10 to 10 volts to 6 volts it is falling because the discharging time constant is small. If time constant increases, then the uh, by the time the input completes one cycle, the capacitor is slowly discharging, so it is able to fall up to 8 volts only instead of 6. By the time input reaches just is exceeding 8 volts. That's the idea. And third case, it may be some 9.5 volt or 9 volts. And here it may be some 9.8 volts, something like that. Okay, like this we can see. So the time constant should be as much large as possible. RL, discharging time constant, I can say. So if RL is very large, then we can see better results. Ideally, large means infinite. If RL is infinite, the output is 5 volts DC, we can see. Okay, so here as the time discharging time constant is right, implies definitely tau d1 is less than tau d2 is less than tau d3 less than tau d4. Fourth diagram I have not written, but okay, we can understand that. So if RL is very large, we can see much better results, best possible results. So what we can observe from this, if RL is very large, then okay, we can see minimum AC and maximum DC, or we can observe best possible DC. Okay. And one more thing, what about the charging time? Oh, sorry. Here, charging interval, sorry, oh, small mistake I did. Here in the first case, it is from 6 to 6, I can say. Next case, 8 to 8. Next case, 9 to 9. Next one, last one, 9.5 to 9. So 6 volts to 10 volts, this is the charging time in first case, but charging time constant is RF into C. In the second case, the charging time constant, charging time is 8 to 10, which is less compared to the previous case. And discharging time is increasing, is it not so? 6 to 6, anyway, I can say from this point to this point as one cycle T, which is equal to charging time plus discharging time. And charging time means it is the charging time tau c, sorry, Tc, not time constant, time. Charging time and discharging time, it is Tc and it is Td. Friends, don't think it is time constant, it is time interval. Whereas in the second case, charging time will be this much and discharging time will be this much. So the charging time is decreasing and discharging time is increasing. And coming to the third case, the charging time is much less, Tc, and discharging time is increasing like anything. And the last case, very much negligible charging time, 9.822, and discharging time is extremely high. I hope you get the point. But charging time constant is not changing, but the interval is decreasing. Discharging time constant is changing, accordingly the time interval is increasing. Okay, please do observe this point. So the effect of RL, if RL is small, then both charging time is large, discharging time is less, but the overall period remains the same. If RL is very large, charging time will be less, discharging time will be more, but the period, overall period will never change. See, 10 to 10, it's one cycle, or 9.8 to 9.8, one cycle, and 6 to 6, it is one cycle. Time period is not changing, but the charging and discharging intervals are changing. Okay, and in which case you are getting better results when time constant is very large. That time diode conduction period is very less and discharging time interval is almost equal to the time period. So every case, in all the cases, T is equal to charging time plus discharging time. Okay, so this is the idea. Now to see the best possible results, what we can do, we should see that RL is very large. If RL is very large, then we can see the best possible DC, and charging time will be small and discharging time will be large. So now I am taking the case where time constant is very large. Okay, so choose for the further analysis, for let us consider a case where RL is very large, so that charging interval is very less, very small, and discharging interval is very large. Okay. Time period does not change. Time period is same as that of input only. And one more thing, the average or DC value is very large. The average or DC value, also the DC component, high, is large. DC is large and almost it looks like a DC only, almost like a perfect DC, means AC component is extremely less, means ripple component is very less. Okay. Also DC component is very large and AC or ripple component is very small. That's it. This is the idea here. Okay, now I'm considering that case and analyzing it. So in steady state, what we can observe is Vs, right? We know the half wave rectifier circuit. Without a capacitor, we know how the waveform comes. This is the waveform we can see without capacitor. Only with RL we can see this. But with the capacitor, what we can see, with the capacitor, we can observe this kind of waveform, output waveform with larger time constant. Okay, correct. Now this, it has to go like this. Okay, so that it has some DC or average value which comes in between. Average value is in between maximum and minimum. Maximum is Vm. Okay, and output waveform is something like this red color one. So what about IL? IL is equal to V output by RL, load current. It is V output by RL means whatever the shape we have for V output, almost the same shape we can see for IL. Here there is a mistake, friends. This is a mistake. Is it not so? Okay, that's it. It should not touch here. There is a mistake. It should go this way. This is how we can see, because V output is equal to IL into RL, or IL is equal to V output by RL. V output shape is something like this triangular waveform, and IL is also a triangular waveform. This is one important point to be observed. Okay, fine. And one more thing. Here, if you observe this, it is a combination of AC and DC, no doubt about it. VDC, you can see. AC, is it possible to see? No. And what is that AC component is my concern. Even earlier rectifiers we studied, half wave rectifier, it is like this. And DC value, we can show it by means of an imaginary line whose value is Vm by pi. But is it possible to take the AC value? For finding the AC value, what we do? We use Fourier series expansion. That's it. We cannot see it on paper, but we can calculate it. Okay, using the Fourier series expansion. We know in Fourier series, output is given by, right, A0 plus sigma n is equal to 1 to infinity an cos n omega naught t plus sigma n is equal to 1 to infinite bn sin n omega naught t, where an is equal to, right, A0 is equal to 1 by t. Average value, no, it is simply 1 by t integral 0 to t V output of t dt. We have been calculating whose value is found to be Vm by pi. And an formula, it is not 2 by t integral 0 to t V output of t cos n omega naught t dt, and Bn is equal to 2 by t, right, into V of t, 2 by t integral 0 to t V output of t sin n omega naught t dt. Okay, some formulas and all. So this whole thing gives us the AC component. We are well aware. And in a similar fashion, here also the output is, right, appearing something like a triangular waveform. It is almost like triangular waveform. Charging, discharging, charging, discharging. So DC component we can able to show. What is AC component? Again, Fourier series and all we need to. Do we use it? Not required, but still we can find it. And here, one more thing I would like to take here, that okay, just place is not permitting. I am writing here, friends. See, suppose I have some sine wave like this. It is some 2 sine omega t. It is simply pure AC signal. We know it is pure AC. Suppose I take a signal like this. It is 3 plus 2 sine omega t. It is a combination of DC and AC. We are well aware. It is the DC component and it is AC component. Combination of DC and AC. Okay. So which appears like this. A similar story I can take even for triangular waveform also. See, I have a triangular waveform like this. Just as an example, I'm writing. Right, whatever you have for positive cycles, the same thing you have for negative cycle as well. Let us assume. Means it is pure AC signal. And the same triangular wave, if I write like this, like what I write for this side, it is some triangular waveform. Now what I can write, it is, so maybe, right, I do not know what is its peak to peak amplitude, maybe some 2 to minus 2, let it be. Then it is like 3 volts, 5 volt and 1 volt. Means I can write 3 plus our triangular waveform. Then it is DC and this is, it is a combination of DC. The same point I am using here. Our overall waveform is like this, which is looking like some triangular waveform. Okay. In that, DC component means green color one, and AC component is like triangular waveform. Is it not so? It is visible. Here, AC component is not visible but can be calculated. Here, AC component is visible. That is the only difference. Here, I can say AC component not visible but can be calculated using Fourier series. Here, AC component is triangular one, so which is visible. That's the difference. And why it is a triangular? You may be having a doubt. I will explain. Right? It takes time. Just we need to wait. Okay. So AC component is a triangular wave and DC component is visible. Here AC component is not visible but can be calculated. Okay, in this example I am not calculating the AC component, but still I can find the ripple factor, RMS value of AC component, etc. We will see that how it is so. Okay, and I am taking a case where the time constant is very large, where I can see very small conduction of the diode, and maximum time the diode is off. Charging time is very less and discharging time is very large, so that the output almost appears like a straight line. Okay, and few more things I would like to use in this analysis, that is the RMS value of a triangular wave. If you take it, because I mentioned triangular wave, peak amplitude by root 3. Otherwise, peak to peak amplitude by 2 root 3. Please do observe this. This is what we can do it. And one more thing, e power minus x is approximated to 1 minus x if x is far less than 1. Anyway, it is a fraction. 0 less than x far less than 1. Okay, and cos theta is equal to 1 minus theta square by 2 factorial if theta is very small. Just I will be making use of these points while analyzing the half wave rectifier with capacitor filter. Okay, please do remember these points. Right, the complete analysis will be based on these things.